Why are diagonalizable matrices important for us? Why are we stressing with diagonalizability? Because the fact is this one, and it's going to be very easy. If we consider x dot is equal to ax, and I start along v2, and v2 has lambda 2 is equal to minus 0.5, you should be able to see immediately the trajectory, how it looks like. How will the trajectory look like? I will have the dots that are aligned with v2, true, and they are going to be actually in the opposite direction because I've got minus 0.5. It means that somehow I evolve along this eigenspace, true? And then we go to 0. And if I start here, and this one is plus 2 as lambda 1, I will have something that explodes in this direction, true? Diagonalizability means that I have n independent subsystems, each of them working independently of each other. Do you see it? Think at this we got the intuition that whenever we can diagonalize, it means that if I take up as a basis the basis formed by the V's, I've got a diagonal system, a diagonal transformation. Are we together on that? We're together on that. Perfect. So let's plot directly something that looks like this one. V1, V2, V3. If I've got plus 1, minus 2, minus 3, if I start here, I will go here. If I start anywhere else, I will explode. You see it? And I can combine things. For example, let's pretend that it's like this. It's going to be easier to visualize. V3 associated to plus minus 10, and V2 associated to minus 100. Okay? If I start in this plane, how will the trajectory look like? Will it look like this one, or this one, or you do not know? Along V2 is minus 100, okay? Along V2, we have a system that becomes essentially x dot is equal to minus 100x whenever I start with x in V2. Do you see it? It means that this trajectory here goes to 0 super fast. This trajectory here goes to 0 slower, with a time constant that is 1/10 the other time constant. True? And if I start here, it means adding up this trajectory plus this trajectory. And I've got linearity. You see that the linearity part is important. Are we together, people? Why is diagonalizability important? Diagonalizability tells us that we have n independent subsystems, single dimensional. It means that the evolution x of t, if I've got diagonalizability and I have this system here, can I see something like this one, t e minus 3t, some vector? Yes, no, I do not know. I have diagonalizability. A is diagonalizable, okay? That means I've got n independent subsystems. Can I have a t appearing in my free evolution? A single dimensional system, a first order ODE, how does it behave? X dot is equal to alpha x. How does it behave? E alpha t. True? Does it have some t's, this stuff here? No. Single dimensional systems are exponential. True? Are we together? If I've got an evolution that is a sum of one-dimensional systems, it's going to be a sum of exponentials. It cannot have a t. Do you see it, people? Perfect. Then we do this example, and then I think we are going to be very, very happy. cylinder rolling on a plane without friction. We saw this. P of t is going to be equal to what? T V0 plus P0. True? This is a mechanical system, and if I write it in state space, PV dot is equal to APV. This A corresponding to this system, is it going to be diagonalizable? Yes, no, I do not know. Discuss. So people, what would you say? You would say yes, no, diagonalizable, yes, no, I do not know. Everybody say no, because we have this T. But indeed, if we think at the matrix, how does this matrix look like? We have P dot V dot is equal to 0, 1, 0, 0, P, V. True? Is it diagonalizable? No. You see? You see why this stuff here is very important? You see why this example is extremely important? Is the first example where, from a physical system, we touch the effect of non-diagonalizability. We see it because there's a T, but this T doesn't come randomly. It comes from the geometric structure, Jordan structure of A. How much are we together, people? I hope it's a moment where you kind of see how a glimpse of things connecting all together and going everything back all together. You see? You see? Now we continue the course. Next 2 weeks, we put even more things together, and everything is going to be essentially one unique source. Good. Questions, people? Yes.
What does this tell us about the system that it's not like
I didn't get the question, sorry. I didn't get in which sense.
What does it tell us about the system if the state matrix is not diagonalizable?
You do not have independent subsystems. You've got subsystems for which the dependency is non-first order. It's multiple order. And it means that somehow you've got poles that are repeated poles.
Does that mean that in essence like that position and velocity are connected?
Yeah, there's a connection here. But this is a special one. It's a special one. In this specific case, they are kind of connected through this double integration part. If we think at spring mass systems, there we will have two eigenvalues, and they're going to be either real or complex conjugate. We are going to go through, I bet, next week, because there's the kind of the examples of the spring mass system that is like the prototype of the stuff here, because this is a generalized spring mass system with zero friction and zero spring. We're going to get. Another question.
I have doubts regarding the when we have matrix that is diagonalizable. For example, in the plot that you showed us, it was like that if we are on the basis, new basis, we just follow we stay on that trajectory, right? But if I'm not starting from there, will I have also the contribution of? I think I won't have the contribution, but from the equations. But by looking at it, I would say I will.
So what happens if I'm outside? It happens that V1, V2, V3 is a basis. True? It means that I can divide x in 3 contributions, this plus this plus this, true? Together, because V form a basis, true? Then it means that since this is a cause, that is a sum of causes. And then I will have effect, effect, effect. The end effect is going to be the sum of effects. This is linearity. The fact that I've got diagonalizability means that I can express my x as a sum of n components, where each component is essentially along the eigenspace and will evolve by itself. And then the trajectory is going to be given by the sum of those n effects.
But that isn't what we already said at the beginning without talking about diagonalizability, when we said that those are the projections of...
But not always you've got the possibility of putting x as a sum of n components.
Okay.
You will have something that is, you write it as a sum of eigenvectors and generalized eigenvectors whenever you do not have diagonalizability. That's why it's important to understand the generalized eigenvectors, because they will correspond to some movements that are going to be specific movements that are going to be t to the power of m e stuff. That's why the generalized eigenvectors are going to come back. We saw them up to now for, we cannot diagonalize. Eventually, we will see that they give rise to those stuff here. Spoiler, the biggest m that I'm going to be finding associated to a certain alpha is going to be equal to what? Bet. Multiplicity in the minimal polynomial. We are going to see it. Don't worry. Don't worry. It's a spoiler. Don't worry. We are going to see it in a good way. Other questions? No? And then